When you get further on in math in college, past calculus, you will enter the realm of problems whose derivatives and antiderivatives cannot be solved by any direct means. There is no function, there is no formula that will get you from the question to the answer. The kinds of math that you'll be doing there will give you not a formula or function, but an infinite series that describes your answer. The reason you couldn't find it using traditional calculus methods is that it was literally infinite. If you've got a converging series, then you can use the properties of series and sequences to get an answer. If not, then the infinite series is as close an answer as you're going to get. And if you want anything more accurate, you'll just have to sit there typing in extra terms into your calculator until you've reached the tolerance that you've set. That is to say, until your tolerance for error runs out at 8 or 12 decimal places. Without being able to derive them ourselves, we're going to have to do our Taylor's series by pattern recognition. Torah meets Sinai, we got it from our forebears in advanced math classes before us, and once we see the pattern, it's pretty clear how it expands. The Taylor series for e to the x, the natural base, starts innocently enough, and after the third or fourth term, you can see how the pattern is going to start to go. See where this is going? Finish the series yourself. Got it? Fine. And so on and so forth. Let's do another one. Let's do the Taylor series for sine. See the pattern? Fantastic. Pause and finish it off on your own. See how the sine series relates to the e to the x series. It said that the sine series is simply the odd number of terms from the exponential base series. You're perfectly right. That would leave cosine as the even number of terms, and we're going to have to work the pattern backwards from here. If this is the x to the second over 2 factorial, this is presumably x to the first over 1 factorial, aka x over 1, which is just x, and that would make this x to the 0 over 0 factorial. That doesn't make any sense. Well, fortunately for us, the writers of the factorial defined the factorial not only as a step function, but as a piecewise function. 0 factorial is defined as 1. 1 factorial is defined as 1. Over here, with the higher integers, is where the pattern actually sets in. So yes, this is x to the 0, which is 1 over 0 factorial, which is definitionally also 1 in the piecewise function. And we can continue the pattern very nicely here in the evens. Notice the sign change. We've got odds and evens here, but we also have a series that flips the sign every term. Pause and see what you can do within the realm of real numbers to combine sine and cosine to get e. Watch those SIG ends. Pause, press play when you're ready. No luck, huh? Don't take it too badly to heart. It's not possible within the realm of the real numbers. Even if you combine these two, starting with cosine because the 1 is the first term, and going nicely on here, you'll find these sign errors simply drive you nuts. There's nothing we can do in the realm of real numbers that will prevent 2 out of every 4 of your signs from not being the ones in the e to the x series. They don't even flip either or the way they did in sine and cosine. To make this function truly periodic, that is, to go in a cycle of 1, 2, 1, 2, or at least 1, 2, 3, 4, is to leave the realm of reals behind and go into the complex plane. Write out the series for cosine plus I sine, cis as you called it in pre-calculus, and compare not to e to the x, but to something else in the complex plane. Take a second and see if you can recognize the pattern, then press play. Learning about cis and argon diagrams as part of your exercise in the complex plane is that cis, cosine plus I sine, is really e to the ix. Check it out. E to the 0 is 0. Next term, we have ix. Instead of regular x, we have I squared, which is negative 1. X squared over 2 factorial. We have I to the 3rd, which is negative I, over 3 factorial. We have I to the 4th, which is just 1. X to the 4th over 4 factorial. I to the 5th, we're back around to I again. X to the 5th over 5 factorial, and so weiter. The pattern works. Fond of setting x equal to pi so that they can say with great fanfare that e to the I pi, here, what's the cosine of pi? Well, cosine of pi, that's 180 degrees, plus I sine of pi, again, sine of 180 degrees. Together, you're going to get negative 1. Now, I usually just write it down that way, but the mathematicians say, no, wait, add 1 to it. And what do you get? You should be getting 0. One of the most famous equations in all of mathematics, and mathematicians just adore it because it's got all the numbers you need to survive as a human race right here. It's got the integer, it's got the placeholder, it's got the natural base. That's everything that has ever grown in an interesting way. It's got all the fundamentals of geometry that you can't get with a ruler, that's pi, and it's got your bridge to the complex plane. Beautiful. Having gone for an interesting adventure in math, let's apply this to physics, namely to the question of simple harmonic motion as it's going to come up when we move to the simple pendulum. In our physics, we're going to encounter the small angle approximation, where otherwise sensible and law-abiding physicists are going to simply start spraying falsehoods all over the page, leaving us with the question of what on earth they think they're doing. So here it is, the small angle approximation. Define x as 0 point something really, really small. How small? You'll figure it out yourself in lab. Sign of something really, really small. Previously, we had to use the unit circle, but now we've got a Taylor series. Check it out. The first term is going to be x, whatever that was. The second term is going to be whatever you get when you take an incredibly small decimal, raise it to the 3rd power, and if that's not enough, divide by 6. The 3rd term is going to be taking your really small decimal, raising it to the 5th power, and then dividing it by 120. I don't think we really need to bother to go on because it's pretty clear that this was already small peanuts. This is going to be pocket change, and this, considering how small the decimal was already, is going to be absolutely negligible. The small angle approximation, as practiced in simple harmonic motion, is defining really small angles, and notice that in order to do this, x has to be in the radian system. None of these cosine and sine geometric relations work in any system besides the radian system, the one that takes advantage of this pi and allows you to go from angles to distances and back again. You will notice that for sufficiently small angles, the first term is really going to be the driving term of the series when everything else isn't going to make any real difference in the 3rd sig fig. We happen to encounter a differential equation which is not solvable using the amount of calculus we know at the moment, and the problem is a sign that's sitting there precisely where no sign should be. notice that there's going to be potentially a difference in the solution for very large angles and for very, very small decimals in the radian system, such that for a given level of uncertainty that you're willing to tolerate, remember our tolerance as before, you may be able to approximate the sine of the angle simply with the decimal itself. I suppose there ought to be a small angle approximation for cosine too, such that by the time you finish squaring that decimal and cutting it in half, there isn't really much left but a few peanut shells. So that the small angle approximation for cosine, this was just what we got in geometry when we looked at the unit circle. So we'll focus on sine for the time being.